This episode is brought to you by Brilliant. Have you ever noticed those peculiar details in everyday objects? A seemingly arbitrary texture or an odd geometric flourish, or maybe a component that appears superfluous at first glance. Engineering history is filled with these quiet solutions, each one solving a specific problem most never knew existed. Here are some particularly elegant examples where careful observation reveals the layers of hidden purpose. Auxetics are a little-known class of non-intuitively behaving metamaterials that are found in many consumer apparel and footwear products, as well as prosthetics and medical devices. Fundamentally, auxetic materials do something that seems to break the rules of physics. They get thicker when stretched instead of thinner. This characteristic is known as having a negative Poisson's ratio, where axial elongation causes transverse elongation. This is in contrast to an ordinary material where stretching in one direction causes compression in the other direction. The history of artificially produced auxetic materials dates back to 1978, when Berlin researcher K. Peach conceived of the diamond fold structure. While Peach didn't use the term auxetic, he was the first to describe the underlying lever mechanism and its nonlinear mechanical reaction. The field gained momentum in 1985 when A.G. Kolpakov published the first example of a material with a negative Poisson's constant. This was followed by a groundbreaking 1987 paper on foam structures with a negative Poisson's ratio by Roderick Lakes from the University of Wisconsin-Madison. The term auxetic itself wouldn't come into common usage until 1991. Auxetics would make its first appearance in footwear around the early 2010s when major sneaker companies started exploring these structures for athletic shoes. This came after decades of academic research, during which interest in auxetics grew exponentially, from just one publication in 1991 to around 165 publications by 2016. Nike was among the pioneers in commercial applications, implementing auxetic patterns in their free RN motion fly knit shoes, creating soles that could expand multidirectionally during running. Auxetics derive their novel property purely from geometry, not exotic materials. They're designed as low-density cellular structures that incorporate hinge-like areas within the auxetic microstructures that flex. The structures are built using patterns like rotating squares, reentrant honeycombs, and double arrowheads, with one particularly successful design in footwear being the rotating triangle structure. At macro scales, these structures increase their overall volume when compressed or stretched. In sneakers, this principle allows the sole to expand and adapt when compressed, creating a more responsive cushioning system, distributing force across a wider area. A properly designed auxetic structure can absorb up to 40% more energy than traditional materials, while using up to 70% less material. Auxetic properties appear in both engineered materials and in nature, though through different mechanisms. While human-made auxetic materials rely on carefully designed geometric patterns, biological auxetic materials achieve similar properties through different cellular structural arrangements. For instance, the nuclei of embryonic stem cells exhibit auxetic behavior during their transition state. These properties are also observed in cat skin, human tendons, and blood vessels. Despite its effectiveness, the manufacturing process for auxetics is incredibly complex, requiring precision 3D printing or advanced molding techniques. The patterns must be exact. Too much or too little material in any one direction can negate the auxetic effect. Despite these current limitations, its effectiveness is currently encouraging ongoing research on scaling up the concept to large structure uses, such as for buildings and bridges. The automotive glass industry as a whole is packed full of trade secrets and little-known manufacturing techniques, but one feature that is quite obvious to the public serves an obscure dual purpose. The distinctive gradient pattern of black ceramic dots on car windows, known as the fritted edge, represents a clever engineering solution that emerged during the 1950s as a result of the automotive industry's struggle with glass manufacturing. This innovation, which was fully adopted by the industry in the 1960s, was initially developed when automotive manufacturers faced challenges with thermal stress distribution during the glass tempering process, though it simultaneously offered an excellent secondary solution to durability issues caused by the exposure of urethane adhesives to UV light. During the tempering process, automotive glass is heated to approximately 620 to 650 degrees Celsius, or about 1140 degrees to 1200 degrees Fahrenheit, before rapid cooling through pressurized air nozzles at roughly 1000 liters of air per second. During this process, the glass experiences critical temperature differentials that can create stress points exceeding 69 megapascals, or about 10,000 psi. The ceramic frit dots, which have a thermal expansion coefficient around 90% that of the base glass, create controlled stress distribution points that help prevent random stress accumulation. The ceramic frit pattern is applied through a specialized screen printing process after the glass is cut to size, but before it's bent and tempered. The ceramic frit material starts as a thick paste, typically consisting of a mixture of 65 to 75% borosilicate glass frit, 10 to 15% black oxide pigments, and 10 to 20% organic carriers and binders. This mixture is then applied using a precision mesh screen printing process directly onto the flat glass surface. The dots themselves are typically screen printed with a target diameter of 0.8 to 1.2 millimeters near the frit band, gradually decreasing to 0.4 to 0.6 millimeters towards the viewable area, with spacing that increases proportionally to maintain optimal thermal distribution. Immediately after printing, the glass passes through a drying zone where the solvents evaporate, leaving the pattern temporarily fixed in place. During the tempering process, when the glass is heated, the ceramic material melts and permanently fuses to the glass surface while the organic components burn away. During the firing of the ceramic frit, surface tension forces cause the initial square printed dots to form perfect hemispheres. This natural formation process, governed by the surface tension of the molten ceramic material, creates the required optimal stress distribution dot. The advancement of this technology during the 1970s coincided with the development of polyurethane adhesive systems for windshield bonding. Engineers discovered that the frit texture significantly improved the long-term durability of these bonds by providing an excellent surface for adhesion while protecting the adhesives from UV exposure and reducing localized thermal expansion. It also offered the additional benefit of providing an additional adhesion surface for concealing unsightly manufacturing elements like mounting brackets, safety modules, and it offered the ability to incorporate additional features like heating elements for defrosting or antenna elements for radio reception. Modern automotive glass manufacturing uses sophisticated thermal stress modeling to perfect the dot pattern design, with most adopting a honeycomb-like pattern at 60-degree angles, which prevents visual distortion and evenly spreads out heat stress, particularly in more complex glass shapes. In newer vehicle safety systems, these dot patterns have even evolved to be invisible to radar and LiDAR sensors while still managing heat stresses. In industrial processes, every additional control and sensing component that is required in a system inherently adds a new point of cost, service requirements, and potentially hidden variables and consequences. A common approach is to seek simplicity through the inherent properties of a material. Curie point heaters are a little-known example of this approach. Named after Pierre Curie, who discovered the principle behind them in the late 19th century, the technology is based on the Curie temperature, the critical point at which ferromagnetic materials lose their magnetic properties and become paramagnetic. The heating process involves surrounding these metal alloys with copper coils that generate an alternating magnetic field. This field typically oscillates between 50,000 and 10 million times per second. As the magnetic field rapidly switches direction, it causes the atoms in the metal alloy to move back and forth, creating friction at a microscopic level. This friction generates heat, with more heat being generated the faster the field alternates. When the metal reaches its Curie point temperature, it becomes paramagnetic, essentially becoming nearly magnetically invisible. At this point, the magnetic field passes through without causing friction and subsequent heating. As soon as the metal cools even slightly below its Curie point, it regains its magnetic properties and begins heating again. This creates a natural self-regulating heating system that maintains a precise temperature without any external control mechanisms, making it one of the most reliable heating solutions in industrial applications. The first major application of Curie point heaters emerged in the 1960s and 1970s, primarily in soldering equipment and plastic welding tools. The technology's ability to maintain precise temperature without complex control systems made it particularly valuable in manufacturing processes where consistent heat was crucial. Modern industrial implementations often utilize specialized ferromagnetic alloys like iron nickel and iron cobalt, or more complex compositions that include trace elements like chromium, silicon, or manganese to optimize specific properties. These alloys are engineered to have specific magnetic permeability curves that sharply drop at the desired Curie temperature, enhancing temperature control precision to within 1 degree Celsius in some applications. Curie point heaters also have the benefit of fast temperature response, with heating rates approaching 100 degrees Celsius per second, allowing for some advanced systems to achieve thermal cycling rates exceeding 1,000 cycles per hour while maintaining precise temperature control. The excitation coil design is crucial for efficiency, with the most common applications being cylindrical coil heaters and pancake coils for planar applications. The magnetic field strength typically ranges from 100 to 50,000 amperes per meter, depending on the application requirements. Modern industrial applications have evolved to include sophisticated implementations with alloy recipes specifically designed for common use cases. Medical sterilization systems, for example, operate at precisely 134 degrees Celsius or about 273 degrees Fahrenheit using nickel-copper alloys with 29.5% copper content, while plastic welding applications often utilize custom alloys with Curie points matched to specific polymer melting temperatures. More advanced systems employ multi-layer heaters with different Curie point materials, allowing stepped temperature profiles, while others can incorporate magnetic field focusing techniques using ferrite concentrators to improve efficiency. In semiconductor processing, some of these advanced systems can even achieve an unparalleled temperature uniformity of better than half a degree Celsius across 300mm wafers. Current research focuses on developing new alloy combinations that can operate at different temperatures or change temperatures more quickly. Engineers are also working on more efficient ways to generate and control the magnetic fields, particularly for large-scale industrial applications where multiple heating zones need independent control. Triboelectric generators represent a little-known but fascinating intersection of classical physics principles and modern energy harvesting technology. The fundamental concepts are derived from observations of the attractive forces created by static electricity on certain materials. However, the deliberate harnessing of this effect for power generation only emerged recently, with the first triboelectric nanogenerator concept being pioneered by Professor Zhongling Wang and his team at Georgia Institute of Technology in 2012. The working principle of triboelectric generators relies on the contact electrification between two different materials. When these materials come into contact and then separate, they develop opposite electrical charges on their surfaces. The efficiency of this process depends heavily on the materials chosen, with common choices including polymers like PTFE, FEP, and PDMS, as well as various metal oxides and conductive metals. The position of these materials in the triboelectric series, which ranks materials based on their tendency to acquire positive or negative charges, plays a crucial role in determining the generator's performance. Triboelectric nanogenerators, or TENGs, operate through three distinct modes, each designed for a specific application. In the vertical contact separation mode, two sheets containing opposite triboelectric charges come together and separate repeatedly. When pressed together, one surface becomes positively charged while the other becomes negatively charged. As they separate, these opposite charges create an electric field, generating a potential difference between the electrodes. This drives electrons through an external circuit, producing an electrical current. The process repeats with each compression and separation cycle, creating alternating current. For this mode to work effectively, at least one of the materials must be an insulator to prevent the charges from dissipating. The lateral sliding mode operates differently, relying on friction between surfaces moving horizontally rather than vertically. As the surfaces slide across each other, the changing contact area creates a separation of charge centers, which generates voltage and drives electron flow. This mode can function either through linear sliding between plates or in a rotational configuration, offering flexibility in design and application. The single electrode mode represents a simpler design that is particularly useful in applications like fingertip-driven generators. In this configuration, one material, such as a PDMS elastomer, interacts with another surface, such as human skin, to generate charge. When the PDMS comes in contact with skin, it receives electrons due to its position in the Triboelectric series. The separation of these charged surfaces from a single electrode creates the electrical output. This mode is particularly practical for applications where simplicity and direct interactions are priorities, though its output may be limited compared to other modes. In recent research, hybrid versions known as three-dimensional Triboelectric nanogenerators, which combine both vertical contact separation and in-plane sliding modes to enhance energy generation, are being explored. Current Triboelectric nanogenerator technology demonstrations can achieve power output densities of up to 313 watts per square meter, with volume densities reaching 490 kilowatts per cubic meter. Their energy conversion efficiency has also proven to be substantial, ranging from 60% to 70%. Since 2013, Zhonglin Wang's team has developed the first prototype rotary Triboelectric nanogenerator for wind energy harvesting. Researchers have also created various specialized designs, including spiral structures for wave energy collection, enclosed systems for underwater use, and multi-layer disk generators for hydropower. Triboelectric nanogenerators do suffer from the limitations of the friction generated between layers, causing a reduction in conversion efficiency and the durability of the device. At present, this technical challenge has limited their current commercial application focus to small self-powered sensors designed to be integrated into moving bodies. Magnetorheological dampers represent one of the most significant advances in commercial adaptive suspension technology, though for the vast majority of consumers, the technology is hidden behind a sports mode button. First pioneered in the early 1990s by Lord Corporation, the technology builds upon the fascinating properties of magnetorheological fluids, which were initially discovered by Jacob Rabinow at the United States National Bureau of Standards in the 1940s. These fluids consist of micron-sized magnetizable particles suspended in a carrier fluid such as synthetic oil or silicone-based fluids, with additional additives to prevent particle settling and reduce wear. The fundamental principle behind magnetorheological dampers is based on the fluid's ability to change its rheological properties almost instantaneously when exposed to a magnetic field. In its natural state, the iron particles are randomly distributed throughout the carrier fluid, allowing normal fluid flow. However, when a magnetic field is applied through electromagnetic coils within the damper, these particles align themselves along the magnetic flux lines, forming chain-like structures perpendicular to the direction of fluid flow. This alignment drastically increases the fluid's yield stress and apparent viscosity, effectively creating a semi-solid state that can be precisely controlled by varying the magnetic field strength. Like traditional designs, these dampers consist of a piston moving through a cylinder, though filled with magnetorheological fluid. The piston contains electromagnetic coils that, when energized, create magnetic fields perpendicular to the fluid flow direction. The piston also features specifically designed flow channels that control fluid movement between the compression and rebound chambers. What makes this system particularly remarkable is its response time of less than 15 milliseconds from command to change in damping force. The first major commercial application of magnetorheological dampers came in 2002 in the Cadillac Seville STS model under the Magneride brand name. This system was capable of computing adjustments up to 1,000 times per second based on road conditions and driving dynamics using sensors that monitor wheel movement, vehicle speed, steering angle, and body motion. In real-world applications, magnetorheological dampers have proven exceptionally versatile. In automotive use, they provide an unprecedented combination of ride comfort and handling performance. During normal driving, the system maintains relatively soft damping for comfort, but instantly stiffens when detecting aggressive cornering, sudden braking, or road irregularities. The system's ability to adjust damping force independently at each wheel allows for sophisticated control strategies, such as reducing dive during braking, minimizing body roll during cornering, and even preemptively adjusting suspension characteristics based on road surface predictions from forward-looking sensors. Newer systems now incorporate machine learning algorithms that can predict and adapt to driving patterns and road conditions, further optimizing the balance between comfort and performance. While magnetorheological dampers have been proposed for civil engineering use, particularly for seismic protection systems for buildings and bridges, settling issues of the magnetic particles have so far prevented their use in larger, slower-moving applications. Their use in prosthetic design, however, has proven to be far more successful as the kinetics involved more closely resemble vehicle suspension systems. Engineering history is filled with fascinating oddities that challenge our assumptions about how things work. These marvels remind us that innovation often comes from thinking outside conventional boundaries, a principle that's just as vital in modern software development as it is in engineering. Coding is full of its own surprising elegance and unexpected solutions, and a great way to develop these innovative problem-solving skills is Brilliant. Brilliant is where you discover the thrill of learning with thousands of captivating interactive lessons in math, data analysis, programming, and AI, designed to unleash your potential and transform you into a confident problem solver. Brilliant is an innovative learning platform that stands out for its use of a first principles approach that enables you to build a solid foundation of understanding. Each lesson is brimming with interactive problem-solving exercises, allowing you to actively engage with concepts. This technique has been shown to be 6 times more effective than simply viewing lecture videos. Moreover, all of Brilliant's content is developed by a distinguished team of award-winning educators, researchers, and industry experts from prestigious institutions such as MIT, Caltech, Duke, and renowned companies like Microsoft and Google. Brilliant immerses you in active problem solving from the start because truly learning a concept requires more than just watching and memorizing. You need to experience it. By engaging in hands-on learning, you'll not only build real-world knowledge on specific topics, but also develop critical thinking skills that make you a better thinker overall. Investing in daily learning is crucial for personal and professional growth, and Brilliant makes it easy and enjoyable. With engaging bite-sized lessons that fit seamlessly into your schedule, you can build genuine knowledge in just minutes a day. Say goodbye to mindless scrolling and hello to more fulfilling ways of spending your free time. A great entry into unique problem solving with code I highly recommend is Brilliant's Thinking in Code course. In this course, you'll develop your mind to think like a programmer and begin writing complex programs to build games and apps, all while honing in a new way of approaching problems with greater logical insight. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/newmind or click on the link in the description below. You'll also get 20% off an annual premium subscription.